we're going to take a look at a technique called photoelectron spectroscopy. Spectroscopy is the interaction of light or any electromagnetic energy with matter. Electromagnetic energy consists of high energy waves like gamma, X-rays, and UV, as well as lower energy waves such as visible light, infrared, microwaves, and radio waves. Just to review, light, like electrons, can have properties of both particles and waves. When light behaves like a particle, we refer to it as a photon. Electrons can be ejected from an atom when they're hit with high enough energy. This is called ionization. Ionization energy is the amount of energy to remove a mole of electrons from their atoms, and it is always positive, since energy is added to the system. You can see in this picture that the ejected electron is now in motion. It has kinetic energy. If an atom is hit with an X-ray of sufficient energy, an electron will be ejected and it will have kinetic energy. Because of the law of conservation of energy, the incoming energy is equal to the energy required to remove the electron plus the kinetic energy of the electron. We can measure the kinetic energy of the photon and the electron, so we can calculate the ionization energy. So let's take a look at a couple of questions. Pause the video and try to answer the 3 questions on this page. Note, I'm color-coding the electrons in the model just to make it easier for me to describe what's happening. Based on Coulomb's law, the blue electron has a stronger attraction to the nucleus. This means it takes more energy to remove it from the atom. If the incoming energy is constant, then the electron with the smaller ionization energy would have the higher kinetic energy, so the green electron has the higher kinetic energy. In the last question, there are a lot of words, but it comes down to this. We can measure the kinetic energy of both a photon and an electron. By rearranging the equation we saw above, we can use subtraction to find the ionization energy of the electron. We can see it's about 9,000 kilojoules per mole. So now let's look at a model of an atom with 3 electrons. The ionization energy of the pink and blue electrons is the same because they are on the same energy level. So let's assume that a whole bunch of lithium atoms are subjected to a high energy X-rays. Each atom loses exactly 1 electron, but which electron is ejected is random. This means that 1/3 of the time the green electron will be ejected, 1/3 of the time the blue electron will be ejected, and 1/3 of the time the pink electron will be ejected. Graphing the ionization energy versus the frequency of ejections, we can see that the higher ionization energy happens twice as often. This graph is called a photoelectron spectrum, and the technique is called photoelectron spectroscopy, PES. Let's take a look at what this graph shows us. First, the x-axis is backwards from what we're used to. The highest energy is closest to the y-axis. Second, based on our model, the nucleus would be at the y-axis. Third, 2 peaks show us 2 energy levels. And fourth, there are twice as many electrons in the first energy level as there are in the second. We can write the electron configurations. 1s2, 2s1. Now let's look at the PES of neon. Pause the video and try to answer both the questions. The first model shows 2 energy levels. This seems to match what we saw in the lithium model. but the data show 3 peaks, so it makes sense that there are 3 energy levels. Also, the little double bar thing in the graph shows there's a big difference in the ionization energy of electrons in the first energy level and the ionization energy of electrons in the second energy level. The second model shows 2 energy levels, but one of them is broken up into subshells. This model is clearly a better fit with the data. If you compare the lithium and neon spectra, you can see that the 1s electron in neon have a much higher ionization energy than those in lithium. This is Coulomb's law in action. The greater the nuclear charge, the higher the ionization energy. Now pause the video and sketch a PES of beryllium. The lithium PES is here for reference. Take a look at my diagram. Each peak is the same height because there's 2 electrons in each orbital. The ionization energy is higher for beryllium's electrons compared with lithium's electrons. This is because the nuclear charge is bigger when there are 4 protons. Now try to draw these orbital diagrams and answer the 2 questions that follow. Pause the video and start again when ready. Here are my orbital diagrams. Also, I've labeled each peak with the energy level, subshell, and number of electrons. Hopefully, you are able to justify the leftward shift of peaks A through D in sulfur with the reasoning that an increase in nuclear charge causes an increase in ionization energy, Coulomb's law. The last peak typically gives people more trouble. Let's take a look at an orbital diagram for the valence shell. We would expect the E peak in sulfur to shift left, but the ionization energy of a 3p electron in sulfur is actually lower than that in phosphorus. The electron-electron repulsion due to a paired electron decreases the force of attraction to the nucleus. Now you have a chance to try some practice problems. Pause the video and try these problems on this page. So all of these. Start the video again when you're ready. Potassium has 19 protons. Calcium has 20 and argon has 18. Calcium, in red, has peaks that are shifted a little to the left due to the increased attraction due to the increased nuclear charge. Argon's peaks are a little lower in energy because there are fewer protons. Also, there is no 4s peak in the spectrum of argon. If we look at the spectrum, we can see that the 1s electrons are highest in energy. And since sodium in blue has fewer protons, there is smaller nuclear charge, therefore a smaller force of attraction. This means less energy required to remove the electron. Now let's get a little mathy. You need a calculator for this part. As you may or may not remember, the energy of a photon of light is inversely proportional to the wavelength. And here is the equation. Pause the video and try the problems on this page. Start again when you're ready to see the answers. Using the equation and constants provided, we can calculate the energy of a single photon of the X-rays used in the experiment. At the beginning of this lesson, we saw that we can use the measured values of the photon's energy and the electron's kinetic energy to find the ionization energy. It's a really tiny number. And in the last problem, anytime we're going from individual particles to moles, we need Avogadro's number. The first answer is fine, but kilojoules per mole is more traditional. Finally, like mass spec, we need to make sure we aren't ionizing air molecules, so scientists use ultra-high vacuum conditions. So that is everything you need to know about photoelectron spectroscopy. Give the homework a try and let me know if you have any questions.